Hi everybody, we're gonna get started in just a second here. Once my cat goes away. Hi everyone, welcome back to Chem 161. I hope that you had a good weekend, that it was productive. I did a little bit of work, actually I did a lot of work, it was exhausting. And I don't really have that much to show for it, because it's just all behind the scenes stuff. So, just some quick announcements while we are here. As you can see on the banner below, exam number 1 is coming very soon. We have flown through the first 4 weeks, and after week 5 ends, exam number 1 gets posted on Monday. Check the syllabus for more information on that. Basically, it will be posted all day. You have 24 hours to complete it. You get 90 minutes once you hit start. It's not intended to be a collaborative effort, so I am going to take safeguards to try and prevent that, but obviously I can't stop you. That being said, please mind the time. There will be a bit of a time crunch on it because there will be quite a few questions, and they will be mostly randomized. So the best way to do well on the exam is to not rely on the help of others, and it's to know the material yourself. So keep that in mind. How much will the exam cover? I believe that we will get to the point today where I will say, hard stop, this is where exam 1 covers. And it's basically when we're done doing math in chapter 3. After that point, there is no more math in this class. So might as well throw it all on exam 1. There is not a study guide that I have prepared. The slides in the online lectures are basically your study guide. So make sure that you are reviewing these. They are online forever. For your use. And yeah, that's really all I can say about it. That's exam 1. Down at the bottom it says quiz 6 is due Saturday. So when I say quiz 6, what I mean is chapter 6. I number the quizzes based on chapters. You have not had 6 quizzes so far. But the chapter 6 quiz will be due this weekend. I wanted to put it before the exam so that you would do it, because the exam problems and the quiz problems will be very similar. And you could have a chance to look at that stuff. So please complete that by the deadline. And there is a lab lecture this week that is going to cover the lab that I posted last night, which is Beer's Law. Beer's Law is a very simple lab. That's really all I can think of. If you have any questions, type them in the chat. I will address them before the class is over. But let's go ahead and get started. Let me get my pen here. So, I believe the last thing that we talked about last week was how people who think that cell phones cause cancer are idiots. Is that right? Because I believe that we're done on this slide. Oops. I didn't mean to actually advance. How many questions on the exam? I don't actually know the answer to that. Whether there are 2 questions or 6,975, I don't think any answer I tell you is going to be satisfying. So it will be... I'm going to take the... I was going to say the Blizzard approach, but I don't know if that's correct. It'll be done... When it's done, and that's how many questions I'll have. So something like that. So yeah, no idea. And I see... Oh, this is going to be great, you guys. I'm looking at my window, and they have a wood chipper. They're going to be, like, grinding up trees during my lecture, because of course they fucking are. Anyway, hopefully that won't be an issue, and if it does, I might take a second and close the window. Alright. So. Sorry, I just hear it now, and I'm just getting angry. Yeah, I'm gonna take a wild guess. I'm gonna guess that you guys can hear the wood chipper outside my door. So I'm gonna do this, and I'm just going to take my headset off. I'm not gonna hit mute or anything, but I'm gonna close my window, which is an ordeal in and of itself. So give me just a second. Actually, you know what? This might take a second, so I'm gonna put the music back on, and we'll take a break. So apologies. I'll see you in a second. All right, I apologize for that. I can still hear it because they have now moved the wood chipper even closer to my window, but I did close it. Um, I'm just looking at the mic to see what it's picking up here. And it's not really picking much of anything, so that's good. All right. So I apologize for that. The issue with my window there, why it took me like 3 minutes, is because I live in a really crappy apartment complex and my window is actually broken. So I have taken the window off and just have the screen there, but then I had to actually get the window, put it back into the windowsill, and then close the window. And even now, it doesn't even completely close. This is the life of your teacher. That's fine. Anyway, let's talk about this laser. So I gave you a few formulas the other day. Let me actually get to the sample problem preview here. And we'll go like, ooh, that's not what I want. Hold on. There we go. That's what I want. So let's just put this on the screen real quick. And then let's go through the formulas that we had covered so far. So there was the first one that invoked the speed of light. And that was this. C equals lambda times nu. Where C is the speed of light. And then lambda was the wavelength. And then nu was the frequency. And now that I think about that, that might be the only formula that we've got so far. We haven't done energy yet. Yeah, that's probably the only formula. Okay. And we know that the speed of light is a constant. Which is this. Something important to note is that this number, when written as an abbreviation, is inexact. However, we actually have defined length and time in such a way that the speed of light is an exact known number in a vacuum. And so if you look this up online, you'll see that it's like 29979 something or other, like that. A bunch of meters per second. And if you use all of those digits, then it's an exact number. But if we round it to this, which is 3.00, that's an inexact number, but that's good enough for our purposes. All right, I know what the wavelength of the laser is. It's 410 nanometers. What is the frequency? So taking my equation, which my pad of paper is a little tilted, so I got to do that. I'm going to solve for the frequency, so that means that frequency equals c over lambda. And then I'm just going to enter in my numbers, and I got to make sure all my units cancel out. So 3 times 10 to the 8 meters per second divided by the wavelength of this was 410 nanometers. I'm just going to write this number here for now really quickly. If you have memorized your metric prefixes like I mentioned earlier on, then you don't even have to do the conversion. You know that this is true. 1 nanometer equals 10 to the minus 9 meters, right? So really what I could do to convert 410 to nanometers is I could do the dimensional analysis, or what I could just do is just tack this on the end here. Because sure, that's going to move this decimal point over 2, and this becomes a 7. But does your calculator really care? Probably not. So you just type it in like this, and it's fine. Once we're at this point, the units cancel. And the only unit that I have left is this divided by seconds right here. So that means that my answer is going to be in per seconds, which I can write like that. I can write the number divided by seconds. It doesn't really matter. Either method is fine. But what is important here is that when you punch this in your calculator, you're going to get a ginormous number. And the reason for that is because frequency for light is an extremely large number. Light oscillates incredibly fast. And so I got 7.32 times 10 to the 14. So a wave of light will oscillate on the order of 10 to the 14 or 10 to the 15 times per second in a visible laser. That's a lot. Oh, I didn't click on the thing. That's what's going on. There we go. Now this seconds to the -1 unit that's right here, that's the same as divided by a unit, so just keep in mind that since it's hard for me to typeset fractions on here, I'm going to be doing that a lot where I have something to the -1 power. Now, for these problems, what I want you to try and do, actually there's a third problem here. What I want you to try and do is use the formula to solve these questions. On the top here, I have a microwave. A microwave just like what lives in your kitchen, probably. So microwave ovens use microwaves in order to heat up things that contain water in them, so like your food. And they have a specific frequency, and that's the frequency right there, 2.450 gigahertz. Tell me what the wavelength of the microwave is in meters. Question number 2 talks about a star. It gives you a wavelength of 500 nanometers and tell me the frequency. Hey, here, and then tell me what color it is. So you'll have to go back to the visible light thing. And then down here's sort of a story problem. What is the radius of the Earth if it takes light about 1/7 of a second to circle it? Now that's obviously only 1 sig fig, so that is an approximation. But you should be able to get a rough estimate of the radius of the Earth. You may have to look up the formula for radius and circumference. So, I mean, you have the internet, so go ahead and try that. Do these 3 problems. We'll go over the answers in just a second. I'm going to see if those wood chippers have left. And we'll be right back to go over the answers very shortly. So I'm actually sitting here watching your guys' discussion. And I do want to point out there's some mistakes in here, but this is really good. I didn't want to interrupt for just a bit. But that said, how many people are finished? If you need more time, let me know by saying so in the chat. Because we can go over the answers now. Now, a bunch of these numbers you could just look up the answer to. For example, the wavelength of a microwave should be known by Google. The color of the sun should be known by you. Maybe not. You look outside and it's cloudy today. So, and then the radius of the Earth. I'm sure that that's known. I don't actually know that off the top of my head, but I have a guess. So let's go over the answers then. Let me get this. And these are all just applications of the same formula that we were using. Where is my pen? Because I just moved something on my desk. There it is. Okay. All right. So we're going to be using this formula a lot, so I'm just going to write it down again. What is the wavelength of a microwave in meters? So if I'm solving for wavelength, that means that my formula becomes C over nu. That's a really bad nu. Let me try that again. And C is a constant. And then the frequency for this is in gigahertz. I want it to be in just regular hertz, because remember that a hertz is a per second. So I could write down 2.450, and remembering that a gigahertz, or giga anything, is 10 to the 9 of that anything. So that's how many hertz, which is this per second, I have. Now this per second and this per second will cancel out, and now it's going to give me a number in meters. And when I do this, you're going to look at this number and say, well, 10 to the 8 divided by 10 to the 9 is like 0.1, right? And sure it is. And so the wavelength that I got in meters was 0.1224, which with 3 sig figs would be 0.122 meters. Now, interestingly enough, this wave is small enough that it can oscillate within a space, and it needs to be able to do that so it can interact with stuff. This is why microwaves are used, and they have to have at least a specific size. So we can use lower energy waves to do things like cook food. It just so happens that this particular wave is also very good at that because it's the excitation frequency for water. But it is interesting to note that the length of the wave does fit in the microwave. If it didn't fit in the microwave, then I don't think that we could use it for that application. If you tried to cook something with like a 1 meter wavelength, you'd have to make a microwave that was 1 meter big. Or it would start cooking things on the outside, and that's obviously not what you want. Let's go to the second question here. All right, I'm going to just hide the first part because that's not important for this problem. All right, our sun exhibits a 500 nanometer wavelength peak. What color is that? Now, in order to answer that first question, we got to go back in the slides. So let's do that really quick. That was on the previous slide here. Now you'll see that this scale only roughly approximates the wavelengths of light. So this is actually not going to be super helpful to us. But this slide right here tells us 400 nanometers is purple and 700 nanometers is red. 500 is a little bit closer to, I would say, the midpoint than I would say either of these. And the middle color between the rainbow, red, violet, what I would say is like yellow-green. So the answer to our question that we have here, just based on that sort of logic alone, is that our sun's peak should be yellow-green. And if you look outside at the sun, you'll definitely see that it's kind of a yellowy color. But it does turn out that the peak light of the sun, the light that is the most abundant, is something that human eyes have evolved to be very susceptible to. That is, when you look at something that is the main wavelength of the sun, it is a color that stands out as very vibrant, and you can depict it very easily. In fact, it is the same color, and it was chosen for this reason, that tennis balls are made of. And you'll know, if you've ever seen a tennis ball, you've noticed that it's like this very neon sort of yellow-green. That specific wavelength is the peak wavelength of the sun. And it was chosen for that because if you're going to stand on a court and someone's going to hit a ball at you 100 miles an hour, you probably want to be able to see it. All right, so that was what color this is. What's the frequency of this? So we can solve this equation for frequency, which is just the same as we did before, but we put the other thing on the bottom. And we say speed of light, that's still the same. And we'll divide by the wavelength. Now, I have 500 nanometers. But again, remember, a nanometer is 10 to the minus 9 meters, so I could just put this in here, 10 to the minus 9. My meters cancel out. I'm just left with per second. And so when I do this calculation, I get 3e8 over 5e negative 9. I get 6.00 times 10 to the 16 per second, which I could also write like this. Either of those is fine. And that's the frequency of the photon. So something that came up earlier, somebody said that something in nanometers was something times 10 to the minus 8, it looks like. So be careful, it's when you do that calculation here. So for example, this is 500 times 10 to the minus 9. This number actually becomes this. And so it's really common to see 10 to the minus 7 when you're dealing with wavelengths. And pretty much anything that has a 10 to the minus 7 meters is going to be in the visible region. Keeping in mind, visible is 300 to 700, but most of the numbers that you're going to be working with are going to fall in that region anyway. All right, the last problem that we're going to do with this involves beaming a beam of light around the Earth. I don't know how this was calculated, or I think it was just like experimentally determined, not experimentally determined, but from the speed of light and from the radius of the Earth, it was calculated that, oh, light could go around the Earth in 7 times per second. And so what we want to do is we want to figure out the radius of the Earth. So we could say that light has a speed and that speed would be in meters per second. And if I times it by how long it takes for my photon to go, then I would figure out the distance that that photon traveled, right? Because the units cancel out. So this doesn't actually involve a formula. This just involves us trying to put these units together in a meaningful way. So let's try that. So I know that light goes this fast, 3 times 10 to the 8 meters in every second. And if it takes 1/7 of a second for light to go around the world, then this should be how many meters it travels to go around the world. And so that is... That's not in scientific notation, calculator. All right, so here's what I got. 4.29 times 10 to the 7 meters. And that should be the circumference of the Earth. Now, if this is our Earth right here, here's what our light traveled. It did this. Whoop. But that's the circumference. I want the radius, which is this right here. And so the relationship between circumference and radius is circumference divided by 2 pi is the radius, or 2 pi r. Because it's pi times diameter is the circumference, right? And the radius is just half the diameter. So what that means is if I take the circumference and I divide by 2 pi, then I will get the radius of the Earth. And if I know what the circumference is, and I divide by 2 pi, I'm only putting parentheses around that because if you're typing this in your calculator, you do need parentheses. Otherwise, it tries to take your answer and divide it by 2 and then times it by pi. I typed the wrong number, or I wrote the wrong number. 6.82 times 10 to the 6 meters. And if you're curious how many kilometers that is, it's about 7,000 kilometers. Now, using that information that we just got, we could go to Google and we could see just how close we are. And let's see here. Radius of the Earth in meters. And they say 6,378 kilometers. Which is remarkably close to what we got, given that we had one significant figure. So I would say that our calculation was successful. All right, those were the practice problems. Any questions on how we use the formula C equals lambda times nu? Let me know in the chat. Otherwise, we're going to keep going. All right. Let's talk about some physical properties of waves, because light is a wave. As we have observed, we can calculate its wavelength and its frequency. Now, a standing wave is any wave that we have locked into a position, into a physical location in space. And there's a bunch of tools that you could use for this, but the simplest ones would be something like a rope. Now, if I have a rope like this and I fix it at two ends, and when I say fix, I mean like you just hold it and your hands remain in those positions and you impart energy to twirl it or twist it or whatever. If you and the person holding the rope at the other end impart energy at a specific frequency, then what you end up getting is a rope that goes around and around and around and around and around. And this is called jump rope. Yes, we're going to talk about jumping rope in quantum mechanics. So jump rope is an activity that children enjoy, and it's very easy for them to get the rope to go in a frequency, but you have to time it right. For instance, you can't just swing your arm around wildly while the other person just stands there. You end up getting the rope to just kind of go all over the place. And if you remember when you were a kid, you couldn't just grab the rope and immediately be the person that holds the rope for jump rope. Like, it took some finesse, right? In other words, what I'm saying is it takes a certain amount of timing and, more importantly, a certain amount of energy to get this wave. If you don't have the right energy, then you don't sync up with your partner. I almost said opponent because you're competing with the other person on the other side, right? You don't sync up, and then you don't get a wave. We're actually going to see that in just a second. Now, if you take the rope and you twist it in a certain way, you can actually get it to have a space in the middle where it doesn't relatively move, and it's kind of like you have two jump ropes. It's kind of like somebody tried to pin it in the middle, but this is actually really hard to do. You have to twist the rope faster, and you have to make sure that your timing is very good. Because you're twisting it faster, it requires more energy. And we're actually going to see this in action on the YouTube video in just a second. Now, these patterns that we're making with these ropes require specific quanta of energy. So when I say quanta, what I mean is I need some amount of energy and just that amount to make the rope do this. If I put too much, the rope doesn't have this peak in the middle and starts bouncing up back and forth. And if I put too little, I end up here. Now, this can go infinitely, and we can have either 2 of these empty spaces or 3 of these empty spaces or whatever, and I just keep adding these extra little jump rope regions. And so this is what the phenomenon of quantization is known as. If you put a certain amount of energy, you get an effect. If you put too much energy or too little energy, nothing happens. You just get garbo. And so what we're going to see in this video, let me show you the video here, is that by putting in a certain amount of energy, we can make these wave patterns happen, and then we can make some observations about them. So let me load the Slinky video here real quick. And then, let's see here, web browser. Is this the correct one? Yes. Okay, so this should be this. All right, and so what this guy's going to do is he's going to swing this Slinky around in such a way that he makes it look like a jump rope. And so this isn't very difficult to do. In fact, any of us could do this. You don't need a PhD in physics. So I'm going to speed this up until he starts rolling the rope. And I have it muted just in case like his voice gets picked up for a copyright claim. So come on, dude. Spin the rope. All right, there we go. So you can see that this looks like that picture that I showed you. Duh, anybody could do this. So this is what's known as a standing wave. And this standing wave would be the simplest wave that you can make because it doesn't have any complications to it. Like if we didn't do anything, that's not a wave. We have to put some energy into it to get it to start. Now what he's going to try and do is he's going to try and put more energy into it to get the double wave. And so if I pause the video, in fact, if I just do this, if I frame forward and backward, you can actually see that the wave is being formed. I think I accidentally skipped ahead a few seconds there. Now he's looking at you while you look at this video, and it's just awkward. But as you can see, if I put the cursor right here, where my mouse is, I missed it a little bit, I guess. What ends up happening is that the space that my cursor is currently at, YouTube, why are you buffering? Seriously, I'm going 1 frame at a time back and forth, and it's buffering. Where the cursor is relatively still. And so that location is known as a node. Yeah, so the reason I mute videos is because at one of the videos, it was the one with the doorbell, with the guy talking about the Rutherford experiment. YouTube actually emailed me to say, hey, your video had copyrighted content. Here's what we're going to do. And the outcome was actually, we're going to do nothing. You just can't claim money for this video. And I'm like, that's fine. I don't want money from YouTube anyway. But if I do that too many times, what might happen is that it might just kill the page. And that would be very bad, especially midway through the quarter. Anyway, so this location where the mouse is right now is my node. And we'll hit play again. Let this play out. And the node is a location where that no matter how much energy he's putting into it, it doesn't move. Now, relatively, because obviously humans are not perfect at generating waves. So now he's going to try this again. He's going to try and get the 3-wave thing going, and that should have 2 nodes. And it's very difficult to do this, but he does manage to get it for just a little bit. And I'm going to see if I can pause it on the... oh, it kind of fell apart there. Let me frame back here. There we go. So there's the 3-node frame. And so you can see that he's trying to make it, but it's actually very difficult to put just the right amount of energy in here. Because as we're going to see when we talk about quantum mechanics a little bit later, as the energy levels increase, they get closer together. And so you end up getting a jumbled mess. And so if you needed to mark the nodes, there'd be a node right here and a node right there for this wave. So the summary here is that waves have nodes. And that we can actually do this in not just 1 dimension, but in 2 dimensions. Alright. Now, this video, I'm going to actually hope the music comes through and doesn't get me copyright strike, because it's kind of good. I mean, it suits this. But we can do waves in 2 dimensions, and that looks like this. Now, considering that this movie has over 1 million views, I'm probably going to get struck for this, but that's okay. Now, I am going to pause this at times just to talk about it a little bit. So what this is doing is this pin right here is connected to a frequency generator, and it sends a frequency through this plate. And what the plate ends up doing is it starts vibrating in such a way that it goes up and down. I'm just showing you this with my hands, but the plate is actually wiggling up and down. Where the plate moves the least is where the sand goes. The sand is moving towards the nodes, because the nodes don't move. The rest of the plate is going up and down very quickly, and so it's getting jiggled into other places. But the sand lines represent where the nodes are. And what we can see is that as the frequency increases, and it's going to print the frequency on the screen here, the frequency goes up, and the number of nodes goes up too. Oops. And there was a puppy, I guess. Oh. It's just showing random videos or whatever. So we can all relax to quantum mechanics. Now, I don't actually know how many nodes are shown on here, because when you get into 2 dimensions and then 3 dimensions, there are multiple types of nodes, which we're going to talk about in a second. So it becomes very difficult to count them. Also, you can notice that the shapes are getting more and more complex as the frequency goes up. And that is just a feature of the mathematics, which is beyond the scope of this class. And it's also beyond the scope of my brain. Like, I know of the formulas, but I can't do calculus, because I haven't done it for 20 years. But you get the point. Hooray, nodes! They exist in 1D and 2D. Alright. We'll see if I get that email from YouTube. Now, on our diagram, the number of nodes is related to what level of energy that we have. So the first thing we're going to do is we're going to assign an energy level to each of these waves. I'm going to call that just n. The simplest one we're going to call n equals 1. N equals 2 has 1 space in the middle. N equals 3 has 2 spaces, and they're spaced about 1/3 and 2/3 of the way across the wave. And then n equals 4 has 3 spaces, one of them at each quarter length. The rule is that for the number that we have assigned the wave, whatever n is, there are always n minus 1 of these nodes. And the node is the region where there is 0 net energy. In other words, it isn't moving at all. In fact, no amount of energy that we put into this makes the node move for that given wavelength. Now, the analogy that we made here when we did the standing waves in 2 dimensions was that the sand tries to move to the nodes. And that's correct. Yeah, so actually, what I should say is that no energy moves the rope at the node. So another way to think about it is that it's not that there's 0 energy to create the node, it's that it's a location where you would need to supply infinite energy to make the node move. Because no matter how much energy you put into it, the node stays still. And so what we're going to learn in a little bit is that electrons follow this sort of pattern, but because electrons are the wave themselves, and not like up here where, say, I've got the sand, where the sand moves to the nodes, the electrons are the wave, so they're actually everywhere except the nodes. Ooh, bizarre, I know. So this demonstration that I'm talking about with all the sand showing where the nodes are, electrons are actually going to kind of do the opposite. They're going to do absolutely everything except that. And this is why quantum mechanics is really spooky and scary, is because everything behaves how you don't expect it to. I'm showing you all this about nodes, and, oh, okay, everything just falls in the nodes. Well, it turns out it doesn't do that. It's the exact opposite. But for these demos, it helps us realize that, yeah, nodes exist. On this diagram right here, you can see in these pictures that on the little readout, we have different numbers that produce different effects. Now, there is no rhyme or reason to what these numbers are for our purposes, so you could just ignore the numbers. All you need to realize is that they are very specific and they are different from one another. And when we hit those specific frequencies, we get interesting effects. For example, right here, I have these like ring... That's not the word ring, that's rig. I have these ring-like nodes. And we're going to call these nodes radial nodes. And the reason for that is because they are some radius away from the origin. In other words, the node is some distance, and it's a fixed distance for that level of frequency. Now, as you increase the energy, you get more radial nodes. So here I have 3 radial nodes at a higher frequency and a higher energy. Now on the bottom here, you can see that I have, here is my radial node here and here, so these are radial right there. But what we also have are nodes that seem to just propagate out from the origin. And these nodes are called angular nodes. And what that means is that if I orient something to be 0 degrees, at specific angles, we have nodes entirely along that axis. And so these are just mathematical functions that come out of 2-dimensional waves. Now in 3 dimensions, what's going to happen is that when we look at a radial node, it's going to end up being a sphere. And when I look at a angular node, it's going to end up being a plane. Because, yes, we are going to look at this in 3 dimensions because electrons live in 3 dimensions. And when I show you the shapes of orbitals, it will make more sense that we have had this discussion. So there are 2 types of nodes, radial and angular. And really all you need to know for now is that these are things that exist. Okay? I'm not going to test you on this explicitly, like, what's a radial node? Like, that's a really vague question. But what I might ask you is, how many radial nodes are there? How is the point that the radial nodes start at determined? It's relative to the origin. So the origin is the pin in the middle of the plate. And so it will be some distance away. So a way that I could kind of illustrate that is, because this is in 2D, it would be like right here. So if I'm right here, if I was holding the rope in 1D like this, here's what my wave would look like. And so this spot right here and this spot right here where it passes through the plate, those are my nodes. And then I just repeat that going all the way around in 2 dimensions. So in this one, I want to say that there are 2 radial nodes over on the left diagram, because there's the outer one and the inner one. But over here, there's one very obvious inner one, there's a second one, and there's a third one. Oh, how is the point that the angular nodes start at? So I have to define something as 0. So if I picked this to be 0 degrees, they would then be spaced out some number of degrees that I would satisfy however many iterations I can get in there. So I think that there's 8 here. So each of these would be 45 degrees apart. In the second, are there 2 radial nodes? This one has 2, so this will say 2 radial. And this one actually has 3 radial. But again, this is kind of arbitrary. I could have chosen a different frequency if I had found a different picture that only had 1 node. All right. So that's our primer on nodes. Now, when we come back, what we're going to talk about is something totally different because quantum mechanics is bizarre. I'm basically throwing at you a bunch of random stuff, and then we're going to talk about how people panicked when they studied all this. So when we come back, we're going to talk about black body radiation, which is actually related to the sun. So let me put the title card back up here, and we'll take a break for 10 minutes. Let's see here. Break time. I don't have a timer open, do I? No, I don't. We got live split. There we go. Boop. All right, so I'm going to start the timer. I'll see you in 10 minutes, and we'll get the music going again here, too. Darn it. Someday I will get it. Alright. So the next thing we're going to talk about regarding light is the notion of something called black body radiation. Now, if you've taken an astronomy class, you will have noticed that a very important feature of interstellar objects is their temperature. If you've played any like spacefaring game or 4X game where like you care about like which solar system you colonize, one of the features of those games often is like, oh, what are the qualities of the star? And like, maybe they're red, or maybe they're blue, or maybe they're white, or something like that. And it turns out that all of those things are linked to the temperature of the object. Any object that has a high temperature will emit light. In fact, it turns out all objects behave in this way. It's just that the light is not necessarily in the visible region. For something like the sun is warm enough that it just spontaneously will emit light in the visible range that we can see. It also exhibits light in other ranges. I'm going to show you a chart of that in a second. This phenomenon is called black body radiation, and the amount of light that comes out will peak at a location based on temperature. Now, if you get a spectrum and you get every possible wavelength, then the spectrum is called what is known as a continuous spectrum. A continuous spectrum has all the different wavelengths all put together, and you basically get a rainbow. Now, this does require that the body that you are looking at be emitting light that is intense enough in that specific location that it registers. For our sun, it turns out that that's the sweet spot for what we can see. Almost all of the light that the sun emits is in the visible region, though there is some UV light and there is quite a bit of IR light. But it peaks in the UV region, or not the UV, I'm sorry. It peaks in the visible region, right around here, where we said tennis ball green was. That's the principal color of our sun. On this diagram, the yellow line that you see is where the light that comes from the sun is on the wavelength. So right here we have dotted lines that indicate that this region is the visible region, and as you can see, this peaks in this region. Now there is a bit of extra here, and I actually can't explain this. I want to say that no, this is at the top of the atmosphere, so it's not the atmosphere doing funky things to it. But you can see that there's a lot of error with these numbers, so like the lines are going up and down all over the place, and it doesn't really smooth out until it gets to this end. But what we have observed is that it does tend to follow the equation for a black body. And the black body equation is, I want to say it's like something with t to the 4 in it or something like that. I don't actually know the equation off the top of my head. But it generates this sort of curve. And if I go to this right here, oops, I haven't cleared that yet. The way that the curve works is in the following way. Let me just put this up there for us to see here. Oops, I went to the bottom of the slide here. So I'm going to just put this over here on the right, and then I'm going to draw on the left. We'll just draw some curve. So if this was our sun, that worked kind of like this. And I believe that's the temperature that it said, but I can't actually do that anymore. I can't see that anymore. If I pick a different color to draw with, let's suppose that I had a colder entity. So like, I don't know. I pick this. What ends up happening is that the peak becomes lower, but it also becomes shifted in this direction. And it'd be kind of like this. And then if I pick something hotter than the sun, I don't know, 6,000? Then it would look something like this. And so what ends up happening is that for black body entities, such as stars, we can predict what their temperature is based on where their peak wavelength is. So for instance, with the sun, this was the visible region where it more or less peaked. So that's right here on this. The blue star that I have here peaks in this region, and the red star peaks more over here. Now, if you remember the spectrum of light that we showed earlier, we had something like this. There was visible, and then there was IR. Oh, no, I'm drawing it where you can't see it. Hold on. There was visible, and then there was IR, and then there was UV. But more importantly, at the edges of these, are colors that you've probably heard of if you've ever heard of any sort of maybe science fiction or maybe descriptions of things moving in space. You may have heard the terms red shifted or blue shifted. Now, red shifted and blue shifted mean that the light that we are seeing is either being compressed in terms of its wavelength, which would be it's moving towards us, or it would be blue shifted where it's stretched, it's moving away. But they all have to do with light. And so there's all sorts of interesting properties that solar entities have. The take-home message that we care about here for blackbody radiation is that entities emit blackbody radiation, and when they do so, they emit it as light that peaks in a region that we may be able to see. And for our sun, it just happens to be here. If the sun was more of a blue star, we would not see as many colors in the red spectrum. In fact, our eyes would probably be evolved to pick up more in the blue and slash UV region. And if we had a more of a red star, we would pick more stuff in the red and less in the blue, and so on. All right, so we know that black body entities emit light, and they emit continuous spectra. Now, there is some interesting stuff that we can observe from this. Now, if you point like a camera right at the sun, and you observe the light coming from its surface, you will get a continuous spectrum just like we observed. But if you point it at, like, say, the corona, or somewhere where there's, like, less gas, like the wispy edges of it, what you might observe are... Oh, I thought that line spectra were coming up next. You know, we're going to talk about line spectra, so give me a second. What you might observe is that you don't actually see a continuous spectrum. What you end up seeing is a spectra that either only gives off certain lines or has the full spectrum but subtracts out those lines. And so this is actually really interesting. This led scientists to ask, well, hold on, what even is in the sun? Hell if I know, we haven't been there. I'm talking as if I were a scientist in like 1800 or 1900. Like, now we know what's in the sun. But back then, they didn't really have an idea. And so they said, well, wait, if the sun is really, 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 really hot, and we excite elements so that they are also really, 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 really hot, will they become black body emitters too? And the answer that they discovered was, well, let's try hydrogen. Hydrogen's the most abundant element in the universe. It's probably what the sun is made of, and it is. And when they did that, they observed that there were only 4 colors that came out. And so that's kind of weird. How the heck do we go from every color in just a black body like the sun to just 4 colors with hydrogen? And it turns out when they examined every other element, they all had different line spectra. And if you combine all of them together, you get a rough approximation of what this would be. So that's interesting. Why do elements generate line spectra? And that was a question that foiled people for quite a long time. They had no idea that what you are seeing on this picture right here is actually the behavior of electrons as they're excited and relaxing up and down over and over and over again. Line spectra leads to predictable electronic behavior within a single atom or a single element. Whereas in a black body, the continuous spectra is just every possible transition for every atom. And so we get every color, at least as far as our eyes can perceive. Okay. I think that might be the last slide in this section, but I still have to go back and talk about the photoelectric effect, which is the last of the weird phenomena that we're going to need to use for a background to talk about quantum mechanics. Yeah, okay, so cool. So I'm going to skip back a few slides. We'll go back to the photoelectric effect. And the photoelectric effect is actually a very important phenomenon because this is the basis of solar power. Solar power is very important, especially today with global warming being an issue and a concern. And if we're going to mitigate temperature increases, we need to reduce the amount of carbon in the atmosphere. And this is one way to do it. You might have heard of this scientist. His name was Einstein. Not very famous, I know. You may or may not have recalled his name. But what Einstein observed was that if you had a specific type of metal and you bombarded it with photons that were a specific type of frequency, interesting effects would occur. And he called this the photoelectric effect. Photo meaning I use light to do it, and then electric meaning what he discovered later was that electrons were being ejected from the metal in just random directions. First, let's talk about the premise of solar power and why this will work as a battery. So if I have my light and it comes in, it hits the metal, and my electrons go in random directions. One of those potential directions could be this terminal. This terminal provides a separation of space between the metal and the terminal where the electron has to move to. Because let's suppose that I have a metal with electrons in it. And I shine light at it so that one of these electrons pops out, which means that this guy is now gone. So in this space is a hole where the electron was, and the charge on that must be positive because otherwise I would violate the conservation of charge. So I've separated my electron from whatever atom it was attached to. Now if I have a wire that connects through a battery, that connects back to this side, the electron must go this direction in order for it to fill in the hole. Now, in reality, what happens probably is that each electron in turn fills in the hole going like this, because all the electrons are mobile. It's not just one electron trying to get back home. All the electrons just move in that direction. And if you keep doing this enough times, you get a current. Electrons are all moving, because one photon will excite one electron, and if we're bombarding it with like a mole of photons, we're going to get a bunch of electrons really quickly. So this is the premise behind a battery. If I can separate charge, I can drive the electron in a given direction. I'm having a brain fart here for which picture I want. So I don't actually need this picture terribly much. We'll just throw it up there. But I do want to take a second to talk about the photoelectric effect. and talk about Einstein's observations, because what he did was he did this experiment several times and noticed the following things. And so the first experiment that Einstein did was he took a beam of light and he shined it at a metal, and he observed that electrons were given off. So we got the photoelectric effect. We'll put that there. Photoelectric effect is PE. And so this was some photon. Now, because the photon has... I did it backwards. Hold on. Because the photon has properties that can be manipulated, wavelength and frequency, he said, I want to play with these and see what I can do to see when the photoelectric effect occurs and when it doesn't. So Einstein took a photon with high frequency and low wavelength. And so he did this. And shot this at a wall. And he observed that electrons were given off. So, okay, high frequency causes the photoelectric effect. Let's try low frequency. And he observed that nothing happened. So Einstein concluded that high energy, or higher energy, ejects photons. Or not photons, I'm sorry. Electrons. Higher energy photons eject electrons. Now, if you remember back to the start on Thursday last week where we talked about light, and I said there were two ways to gauge energy of light. The first one was to increase the frequency. But there was a second way to do that. Does anyone remember what else you could increase to increase the energy of light? It's not the frequency. Let's suppose we kept the frequency constant. What else could we change? Amplitude. Very good. Yes. So with light, what that means is I need to put more waves. So I could do this, like this. And so these are high amplitude waves, and we're going to say for the sake of drawing them that they were meant to be this. Oh, what did I just do? Oh, that's not what I wanted. Hold on. I accidentally clicked zoom, and I don't even know where I've selected that. Let me do this again. In fact, what I'm going to do is I'm going to try and do this down here. All right, so what we're going to do is we're just going to increase the amplitude of this by shining a bunch more light onto the wall. And what Einstein observed is that if he had photons that did not trigger the photoelectric effect, and then he increased the amplitude by simply shining more light on it, nothing's happened still. And oh my god, the wood chipper is back, and I'm so angry. So, in just a second, you're going to hear... And I'm just going to try and ignore it, because I can't close the window, because I opened it earlier. Yeah, it's like it's right outside my window, because it is. Anyway, what Einstein said was that, maybe higher energy doesn't eject electrons necessarily. Because up here it worked, but down here it didn't. And so Einstein came to a conclusion. What if each light packet, which he called a photon, was independent. Because then what would be happening is he would be trying to cause the photoelectric effect with multiple photons hitting the same electron. And the best analogy that I can think of for that happening is if you were at a tennis court and you were playing tennis with a friend and you're both standing on the same side and you say, okay, we're going to have a contest. We're going to have both people hit their tennis ball at this bottle 100 feet away, but both people have to hit it at the same time. And if they can do that, then we'll count however far the bottle moves. Otherwise, it doesn't count. I know this is a really shitty analogy, but this is the best I can think of. The odds of two people hitting a tiny object with a tennis ball are incredibly small. And it's the same thing with light and electrons. Photons are basically really tiny gunshots of energy. And electrons are really, really tiny targets. And one photon can hit one electron. But two photons hitting one electron is virtually impossible, just by virtue of how tiny they are and how fast everything is going and what's going on. So Einstein concluded that the only way that this could be possible is if light was these discrete packets. Otherwise, if light was just a continuous beam, then there would be no difference between having a higher frequency and having a higher amplitude. But he observed that there was only a photoelectric effect when we gave each individual packet high enough energy. And so this photon right here has the requisite energy, but this photon right here does not. So in other words, the photoelectric effect experiment shows that photons of light exist as a sort of particle behavior. There are independent, individual photons. Light is not a continuous stream of matter, or energy, I should say, like we would have thought if it were a wave. And so this revolutionized how people thought of light. So not only does light have wave-like properties, it also has particle properties. And so this is where the photon part of the wave-particle duality, specifically the particle part, comes in. The amount of energy that a photon has is based on either its wavelength or frequency. We just pick frequency because the formula becomes shorter. And so that ends up being this right here. E equals h times nu, or hc over lambda. What the heck is h? H is a constant. It is basically the amount of energy contained per frequency. And that is an incredibly tiny number. This is called Planck's constant. 6.626 times 10 to the minus 34 joules times seconds. And the reason that these units are like this is because the frequency part is per second. The per second will cancel out this seconds part when they're multiplied together, and you're left with joules, which are the unit of energy. I'll leave that on the screen for a second. And so what this means is that we can calculate how much energy a specific photon has, and we can determine a threshold for, oh, this is the amount of energy I need to do whatever. And that whatever might be ejecting an electron, or heating the world, or something like that. In your textbook, there's going to be several terms that are used to define how energy behaves with a system. So I'm going to put a picture on the board here. And this box right here is going to be the atom that I'm looking at that got a hit with this photon. We're going to call that the system. So this is my system. On the outside of my system, literally everything else in the universe, so even this text down here, and this text over here, everything else is called the surroundings. So this is what is known as like a thermodynamic system definition. In thermodynamics, which you're going to learn about 162, we have to define the system and the surroundings whenever we talk about energy. Now, if we're looking at this specific atom as our system here, if my photon comes in, it brings energy, and the system absorbs it. When energy enters the system, we define it as a specific name, and we call that endothermic. Ooh, that's impossible to see. Hold on. You know what, we'll just do that. You guys know where the surroundings are now. I can't even see the highlighter, did I? Oh, I chose the wrong thing. There we go, okay. So when energy is absorbed by the system... Oh, I see what's wrong. I chose yellow as my color for my pen, which is impossible to see. There we go. When energy goes into the system, we call that endothermic. Endo meaning inside. For the opposite process, which would be what's happening when my electron is ejected, right here. So here's my electron. If I throw the electron out of the atom, that requires me to use energy to do that. Energy leaves the system as kinetic energy. And so that's called exothermic. So an endothermic process requires energy to be added to your system. An exothermic process requires energy to be released from your system. So with the photoelectric effect, both of these processes happen one after the other. When a photon is absorbed, the system gains energy. When the electron is ejected, the system loses that energy. The total energy exchanged by both processes is zero, because energy can't be created or destroyed. That would violate the conservation of energy. However, what we can learn is that electrons require energy to get launched out of their atoms. That's an interesting thing to note, considering that we have all these things that we've been talking about nodes and how light behaves as a wave and a particle and these spectra. And for a long time, people tried to put all these ideas together. And apparently we have a few examples to do before I can talk about that, but there is one unifying theory that puts it all together, which is called the Bohr model. We'll talk about that in just a second. Let's talk about how to calculate energy for a photon. What is the energy being emitted by this photon? So we'll put the sample problem up. And everything on my desk is now getting blown away. This is excellent. This is exactly how I wanted my lecture to go. Shouldn't have taken the window back out because I thought they were done. I have stuff to put in the window. Like, I put fans in the window that keep the air moving, but I haven't actually done that yet. Why didn't that work? Oh, because I didn't hit delete. There we go. All right. So looking at this problem, I want to find the energy of the photon when the wavelength is at 635 nanometers. Now, we're starting to get to the point where I'm throwing a bunch of formulas at you. And whenever you're in doubt, if you don't know what to do, write down all your formulas that you have handy. Or just have a page of them. And look for what's being asked. For example, this question is asking us to use energy. So I have to use one of these because this top equation doesn't have energy in it. Of the two things that we have available, we have either wavelength and the speed of light or frequency. Well, I gave you the wavelength in the problem, so we're going to use this formula. So let's figure out what the energy of the photon is. Now, energy is measured in joules, so knowing that will make this easier. I need to have joules when my problem is solved. If I don't, I've either used the wrong formula or I'm lost a unit somewhere or something like that. So just be mindful of that. And now we're leaf blowing because of course we are. Couldn't have done any of this yesterday, could you guys? Nope. Had to do it during my damn lecture, huh? Alright. So that's H. We're going to multiply that by C, which is 3. It's 10 to the 8 meters per second. There we go. And then we're going to divide by lambda, which the wavelength is 635 nanometers, which I'm going to turn into regular meters by doing this. And now I have to see if my units check out. So does everything cancel? Can I get rid of everything except joules? Well, this second and then this second cancel out, which is why I wrote it like this. And then this meter and this meter cancel out. And this is the only unit that's left. Which means that when I punch these numbers in as written into the calculator, I will get the answer in joules. And because it is a single photon of light, the amount of energy should be really tiny. Because individual photons do not do much, right? I can't see the number because my screen is dusty. Let's see here. 3.13 times 10 to the negative 19 joules. I'm not saying anything because I'm... Not because I intended to just give you more time to write the answer, but because I'm staring at this person who's leaf blowing right outside my window and giving him the death eye. Alright, I think he's going away. I don't know what he's doing. There's nothing to leaf blow. Alright. So, for practice here, and it looks like this might be as... Well, you might have 10 minutes after this. What I want you to do is answer these questions while I go get the window and then put it back in the wall so I don't have to deal with this shit anymore. Going back to the spectrum of light, you know how it's arranged by frequency and also by wavelength. I want you to tell me what color of light has the lowest energy and what color of light has the highest energy. And when I say color, I mean within the visible spectrum. And then for question 2, here's a laser with a specific frequency, but it doesn't cause the photoelectric effect in sodium. If I were to change this experiment in some way using one of these 3 options, which one will cause the photoelectric effect to occur? And then finally, take that frequency and turn it into an energy. That should be a pretty simple calculation, so I'm going to give you 5 minutes to do this. That's how long it should take me to put the window back in. And I'll see you for that. We'll go over the answers in just a second. All right. Hopefully that problem is behind me. Let's go over the answers to these questions. So the first thing that we want to do is go back. I gotta go back to the slide with the rainbow on it. So that's going to require me to... That's not going to help me. There we go. Okay. And you can see at the very top here that energy increases as we go from right to left. Wow, that's the best line I've drawn. And what color is furthest to the left because it has the highest frequency? That's purple or violet. What color has the lowest energy because it has the lowest frequency? That's red. So let's go back to that question that we just did. I went past it. Here we go. Okay. All right. So I have the photoelectric effect not occurring with this metal for this frequency. Now, if I increase the number of lasers fired on it, that would just provide more photons with the same frequency, because all I'm doing is increasing the number of photons, not the energy of the photons. So this would not work. And the reason for that is because each photon has the same energy as before. I use a laser with a longer wavelength, but what does that do to the energy? If the wavelength increases, what happens to the energy? What's the relationship between energy and wavelength? Did I ever have to use this in grad school? Actually, all the time. It turns out that light is very, very common. Yeah, that's correct. So whenever you are building a spaceship, you don't want to just put more lasers. You want to increase the power of your lasers. That is always better, because then you can always put more powerful lasers. So higher wavelength, because our formula is up here, E equals lambda, or H times nu equals HC over lambda. If I make this number go up, this number goes down. So that won't cause the photoelectric effect to occur because I need more energy. It didn't occur at this frequency. I need to have higher energy, not lower energy. So if I use a lower wavelength, the opposite is true, and the photoelectric effect should cause it to occur. And then finally, how much energy does the photon from the above laser contain? Let me go to this problem screen so that I can... Okay, so 4 times 10 to the 14 is the frequency there. And that was in hertz, so that is per second. And I know that the formula for frequency and energy is E equals Planck's constant times the frequency, which means that I take Planck's constant. Those dots didn't really appear as big as I wanted. So there's H. We're going to multiply that by the frequency. This is per second. It will cancel out with seconds when they are multiplied together, leaving joules. And when I times those together, I get... I couldn't see that number. There we go. 2.65 times 10 to the negative 19 joules. Oh, I messed up on my sig figs. I was just looking at y'all's answers, and it's like, oh, there's only 2? Yeah, there's only 2 because of this number over here. There you go. 2.7 times 10 to the minus 19. So good job if you got that. All right. To go back on to that question where someone asked, like, hey, how much do you use this? If you go into chemistry or any science that uses instruments that use light, pretty much all the time. What we're covering here is the basis for spectroscopy, which is actually what this week's lab focuses on. Tomorrow, when we're going to talk about light and how it interacts with solutions and talk about Beer's law. Sadly, there is no beer provided by me. You have to provide your own. But the Beer-Lambert law describes how light behaves when you beam it through a solution and how much of it gets absorbed. We're going to talk about specifically what that means tomorrow, and also in the rest of Chapter 3 as it comes up. But to summarize what we've covered in this first section, and yes, we are still in the first section of Chapter 3, light is weird. We have learned that light has a frequency and a wavelength associated with it. We also know that light has an amplitude by taking many waves of light and adding them together. We have learned that light will produce a continuous spectra from a black body, but it will produce a line spectra from elements. And we've also learned that the photoelectric effect is an event that occurs with light and an object that has electrons if the photons have a specific frequency, which means that light exists as a packet as well as a wave. So with all of that information in mind, we're going to take that into the next section when we talk about electronic structure, and it's only going to get weirder. That's all I can say, is that this is very, very strange because we're sort of on the frontier of science here. Like, this is just the model that we have that matches with what we observe in the universe, really. Sabrina, you had a question about the exam, and I missed it because you deleted it. Did you need something? Sorry, I wasn't ignoring you. I just wanted to finish my thought. And now I can't because it's gone forever. That was me sniffling. You got to answer. Okay, cool. Hooray. Let's see here. 2:55? Yeah, I think that's all we got for today. So when we come back tomorrow, we're going to talk about the lab, but when we come back on Thursday, we're going to talk about the Bohr equation. And the Bohr equation is the last thing that is on the exam. It is a way to relate wavelength, specifically inverse wavelength, to orbital theory. And I will have you calculate something from that, and that's the only calculation you have to do from Thursday on the exam. But the calculations that we did today are going to be on the exam. They will be questions like you've seen on the board here. So if the theory is what's confusing you, like, holy crap, this is a lot of terms, but then you get to these math problems and you're like, wow, these are relatively easy, I can do that. You're going to do okay on the math part. The theory, obviously, you're going to have to just look up the terms if you don't know them during the exam, which will cost time, of course, but you do always have that option. So just make sure you know what a node is, make sure you know what a particle is versus a wave, what the terms mean, amplitude, frequency, wavelength, energy, and what all the units mean, stuff like that. I want to thank everybody for coming out to lecture today. I apologize for all the craziness with the leaf blower and the wood chipper and the landscape 101. I wish they would come in landscape like this part of my apartment is terrible, by the way. Like, it's being renovated and just everything is falling apart. So I apologize that all just decided to be done today during lecture. It seems like they're gone now. But thanks for coming out. Is the exam format like the quizzes? Exactly the same. It will be on the same server, so it'll be on Canvas. You open it up, it'll just be that you have 2 hours, sorry, not 2 hours, 90 minutes to do the exam, and you only get 1 day to start the exam. So, like, the deadline is going to be the day it's released. Like, I have a button and it will say available from this day at midnight until 11:59 the same day. And then it will disappear and you won't ever see it again until I have everything graded and I release all the scores. Unlike the quizzes, you don't get to see your answers for the exam because I do want to reuse the exams. The quizzes are just sort of like practice and stuff. But the exam questions will look like what your quizzes look like before I release the answers. It'll just say, "Hey, here was your score," and then that's just how it will be. I will talk a little bit more about that later once you have taken the exam. But yeah, that's really all there is to talk about on the exam. So let me put the title card back up. Oh, it's not break time anymore. Oops, that's my announcement. Break time, timer. There we go. But I will see everybody tomorrow, hopefully, for the lab lecture. Peace out. Have a wonderful evening. Stay healthy. Stay inside. The next lab should be online now. I posted it last night. If it is not online, let me know, because that is an issue. I will look at that very shortly. But I do have a meeting that I have to attend for faculty, so I do have to cut the stream off pretty soon. Any last minute questions, please put them in the chat. Thanks for watching. See you tomorrow.